The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so welcome back to AO3. Happy to see you again. So today we are going to continue the discussion of dispersive median. And there are two questions we are going to ask in this lecture, and we will answer also these two questions in this lecture. So just to warn you in advance, this lecture will have a lot of mathematics. So fasten the seatbelt and follow me, okay? And stop me anytime you don't feel like you understand something, okay? All right, so let's get started. Okay, so today we are going to talk about dispersion phenomena related to dispersion. And last time we started a discussion about how to send information from one place to the other place, right? So what we actually did before was to send square pulse, right? So if I do have a machine which can produce square pulse, then I can define something like this. So over some threshold, which I set, I can actually separate 0 and 1, right? So if I have a pulse which is actually having an amplitude greater than some threshold, and I say, OK, I got 1. And if it's actually below some threshold, I say, OK, I got a 0. And with that way, we can actually send information from one place to the other place. OK, so that sounds all really nice. However, if we work on a dispersive median, which is really very common, for example, light in glass, right, is actually not all the lights with different wavelengths are traveling at the same speed. And also, as we see before, as you see in the PSAT, deep water, and also the strings, which are considering a realistic string with stiffness, right, et cetera, et cetera. The wavelength actually is going to, of the input wave, is going to affect the speed of this traveling wave. So in short, the speed of the wave propagation in a dispersive median will depend on the wavelength of this wave. Okay? So that brings us a lot of trouble because, for example, here we are trying to send the Gaussian pulse, right, through the median. But after a while, this pulse actually become wider and wider because of the dispersion. Because all the components with different wavelengths, which actually construct this narrow pulse, actually are traveling at different speed, right? Therefore, if you wait long enough, all the different frequency or all the different wavelengths pulse, all the different frequency harmonic waves are traveling at different speed. Therefore, you get the dispersion, which results in much wider pulse in the end, okay? And at some point, this pulse is going to be really wide, such that it's actually going to be very difficult to separate 0 from 1, okay? So that's the problem. And we also did some simulation with computer. We do see this behavior also in our computer simulation. If I put in a triangular pulse and let it evolve, and like what we did before, we assume that there's a stiffness in this string system. And you can see that, OK, as a function of time, this pulse is no longer a triangular shape, but you have very complicated structure, OK? So that is actually a problem we are going to try to solve today. And during the discussion last time in the lecture, we also introduced the dispersion relation omega k, and also try to overlap two traveling waves with similar wavelengths, okay? And that will give you bit phenomena, okay? Probably doesn't surprise you anymore. As you can see from this example, you have the beat phenomenon, and you can see that the amplitude is actually varying slowly as a function of position. And if you follow the red point, which is actually associated with one of the peak in this structure called carrier, okay, it's actually moving at the phase velocity Vp, which we introduced last time. The formula for Vp, which is actually the speed of harmonic oscillating traveling wave, is actually defined as Vp equal to omega over k. And the green point, which is actually always at the minima of the distribution, which is actually associated with the envelope, the speed of the envelope, you can see that indeed it actually can move at a different speed. It depends on the dispersion relation omega as a function of k you have in this system. And we call the speed of this envelope, which we construct from these two overlapping traveling wave, to be, we call it as group velocity. And the definition of group velocity is Vg equal to d omega dk. Okay, so that's actually what we have learned last time. Okay, you may ask, okay, what do I mean by group velocity, right? And can I use it beyond what we have done for the beat phenomena, right? So what do I mean by group velocity? Okay, is that really useful? And it's actually which part of the structure I was talking about, right? So in the case of two overlapping progressing wave with similar wavelengths or similar frequency, when we see that the group velocity actually present the speed of the envelope, right? Can we actually learn something more general about group velocity, okay? The second question which we are asking is, okay, now we have this problem of dispersion, right? This square pulse is going to become something which is really wide after some period of time, right? So that's clearly a problem. And how do we actually solve this problem? And how do we actually send information like, for example, music over a large distance from one place to the other place, okay? So that's essentially what we are going to try to understand today. So let's start with an infinitely long string, okay? And this string is actually very long, and this begins from here, and it goes to really some place which is really, really far away. And of course, as usual, I can actually hold one end of the string and shake it a bit. Then I can actually create some kind of pulse, which is going to travel along this string, okay, toward a positive x direction. In this case, I define the x coordinate to be pointing to the right-hand side, and that's the positive direction, okay? So of course, I can hold this string, and I can shake it, and I will create a pulse on this median, which is a string with a constant tension, okay? So I can describe the motion. For example, you can describe the motion of Yen-Jie's hand by a function, right? So you can say, okay, Yen-Jie is somehow doing really a nice job and oscillating at the constant frequency. Like I can say, okay, Yen-Jie is shaking this thing to produce a harmonic wave, for example, right? And now I can actually describe the motion of the hand by f of t. Okay, that's very good. And from what we have learned in the last lecture, okay, we found that basically waves, harmonic waves with different frequency or with different wavelengths are traveling at different speed, right? Therefore, we would like to actually decompose the motion of Yen-Jie's hand into many, many harmonic waves, then attack them one by one, to follow them one by one. Then I can solve this problem. Okay, so that's actually what we are going to do. And that will involve some math which we would borrow from the math department, okay? And before that, I would like to introduce the notation first. As I said, f of t is actually the displacement as a function of time at x equal to 0, right? So basically, I'm holding this string and I move things up and down, and so that actually I move this string away from the equilibrium position, which is actually y equal to 0, okay? Then what is going to happen? What is going to happen is that I'm going to produce some kind of pulse, right? And this pulse, I can actually describe it by a function which is psi, x and t, right? This psi is actually describing the displacement as a function of x and as a function of t, okay? Apparently, if you put x equal to 0, then you go back to f of t, right? Basically, that's the idea. Okay. So what we have learned before we introduce dispersive median is that if I have a non-dispersive median, okay? If I have a non-dispersive median, then things are really simple, right? Because omega over k is actually a constant, which is the phase velocity Vp. And omega is actually just equal to Vp times k. That means no matter what kind of wavelength we are talking about, no matter what kind of angular frequency we are talking about, harmonic wave, harmonic approximation wave is going to travel at the speed of Vp, okay? No matter what's the frequency or what's the wavelength. So that makes our life much simpler when we work on non-dispersive median. In this case, okay, if I have a non-dispersive median, then psi will be equal to, okay, maybe I write it here. If I have a non-dispersive median where no matter what kind of frequency, the speed of the harmonic traveling wave is a constant, which is actually Vp, I can write down psi xt to be equal to f of t minus x over v, okay? Just remember f is actually describing how I actually shake the end, one end of the string, and basically you can see that, what is happening is that my hand is actually generating the shape of the pulse as a function of x, as a function of time, and it can be described by a really simple formula here, okay? So this is actually really nice for non-dispersive. As I introduced before, when we talk about dispersive median, okay? Then if I go to dispersive median, omega is actually a function of k and can be a nonlinear function, okay? So what does that mean? That means if I evaluate Vp, which is actually the phase velocity, which is the formula there, okay, this is going to be omega of k divided by k. That means Vp is going to be a function of k, the wave number, okay? It's not going to be a constant in general, okay? Unless omega is actually equal to Vp times k. In general, Vp can actually be some quantity which is varying as a function of k, okay? Then we have a trouble because that means when I produce progressing wave from the left-hand side end, okay? It's actually made of many, many harmonic waves, right? With different angular frequency, right? So I can shake this like different speed, right? And I can always decompose the motion of Yen-Jie's hand into many, many harmonic waves. The trouble is all those harmonic waves are going to be traveling at different speed. How do we actually describe this? All right? So that's the trouble. And I was really frustrated when I think about this problem, and my friend from the math department say, hey, we have solved this problem a long time ago. Right? So this is not the problem anymore. And I say, oh, what is the idea, okay, you're talking about? And that they actually told me that you should use Fourier transform to attack this problem, okay? What is actually the idea? The idea is that I can now write down f of t, which is motion of Yen-Jie's hand. And this can be written as a superposition of infinite number of waves. I can integrate from minus infinity to infinity, the omega, which is the angular frequency. And each contributing wave have amplitude associated with it, which is actually c as a function of omega. And the actual wave is actually written in terms of exponential minus I omega t. Okay, so let's actually look at this thing really carefully. Okay, what am I doing? I'm saying that I now can shake the one end of the string up and down, according to my will, right? And if I do this for a long time, okay, I can actually describe the motion of my hand by infinite number of harmonic waves, okay, which is actually kind of like exponential I omega t, describing the frequency of these waves. And each of them got the associated amplitude, okay? And you may ask, okay, wait a second. You call this Fourier transform, and I have learned that before, but I learned a different version. I learned a version with cosine and sine, right? And what is going on, right? Actually, they are all the same, okay? No matter what you do, you can actually also do that with cosine and sine. But what I actually found is that actually it is actually easier to deal with exponential functional form. Okay, you can always write exponential I omega t in terms of sine and cosine, and absorb the I into c omega. Right? Basically, things are identical between these two formalisms. So okay, so therefore, in this lecture, I'm going to stick with this functional form. Okay, any questions?
We don't include dx in the formula.
Not yet. Yeah, we are going to include that, right? Because for that, in order to actually okay, so now I actually decompose the motion of my hand into many waves, okay, which is actually, or say many oscillation with different frequency, right? So I actually describe the motion of my hand by infinite number of oscillation with different frequency. And the trouble we are facing is actually all those oscillations are going to be traveling at different speed because of the dispersion relation. Therefore, what I'm going to do afterward is to show you that, okay, I can actually write down the functional form for psi in this general case. Okay, so for that, that's actually what I'm going to do now. So now I would like to know what would be the psi xt, right? Which is actually the position of the string as a function of x and at some specific time equal to t. Okay, and that can be written as I do integration from minus infinity to infinity over frequency omega. Okay, and I have the usual amplitude associated with the angular frequency omega, and the exponential I omega t, okay, minus I omega t, because that's the convention I'm using here. And I say, okay, plus I k, which is a function of omega x. Okay, so now you can see that what I'm doing here is that I'm now I'm making infinite number of progressing waves, right? Each of these exponential function is a progressing wave, okay, with angular frequency omega, okay? And why do I write ik k as a function of omega x here? Is because they are going to be traveling at the speed of omega over k, right? Therefore, I need to actually put k here. And this k is actually not, this k is actually not the independent parameter. It's actually a function of omega. Okay, so we can see that here we do an integration over omega from minus infinity to infinity. Okay, for each omega, you can actually find the corresponding k, right? Because of the dispersion relation, right? Because omega is a function of k, therefore you can always solve the corresponding k, right? Then you put it there, because you are now trying to propagate harmonic wave with different angular frequency at different speed. Then we are done. Okay? That looks like a wonderful solution, and we can actually see how it works for our purpose. Okay? Any questions? All right. So that's really nice, and I can now do a really simple test to see if this really works. Okay, let me try a very simple case. Okay, a spatial case. If I now go back to use this description to describe non-dispersive median, okay, and see what will happen. Okay, now my k as a function of omega is actually rather simple. It's actually omega over v, right? According to omega over vp, right? According to the dispersion relation here, okay? I can solve k, as I was mentioning, right? With this dispersion relation formula. And then I can conclude k as a function of omega is omega over p, over vp, okay? Then I can now put it into this equation, and I'm going to get psi x of t. This will be equal to minus infinity to infinity d omega c omega exponential minus I omega t minus omega over vx. Okay? And we can actually take omega out of this, minus infinity to infinity d omega c omega exponential minus I omega t minus x divided by v. Okay? And you can see that, indeed, this is actually f t minus x over v. Okay, I'm dropping the vp here. Okay, it should be vp all over the place, right? So you can see that now if I have solved the k, the function of omega, and I plug it in this spatial case, which is non-dispersive median, omega over k equal to vp. Then I really calculate this integral. Okay, then I can quickly identify that, I can write the functional form in this way, and this is actually look really familiar to me, because that's actually using this definition, right? F is actually equal to integration minus infinity to infinity d omega c omega exponential minus I omega t. If I replace t by t minus x over vp, then I'm done, right? So I have evaluated this integration, which is actually just f t minus x over vp. So that's actually exactly what we actually guessed from the beginning, right? So if I have a non-dispersive median, then psi xt will be equal to this functional form. Okay, so that gives us some confidence that, okay, at the easy case, it works. Okay? All right. So that's very nice, all sounds very good. But wait a second, how do I actually extract this c, which is a function of omega? I'm in trouble because, this is an infinite integral from minus infinity to infinity, and that means I have infinite number of constants which I have to determine the c of omega, how do I actually do this? Okay. So that is actually another point which I would like to discuss before we actually go ahead and really use this function for the dispersive median case. Okay, so how do we actually extract C as a function of omega? All right, so for that, we really need to employ a few useful formula which are actually documented here. How many of you actually have not heard about delta function before? Okay, a few of you actually have not heard about delta function. So what is actually a delta function? This is a delta function. So a delta function is actually a notation which actually shows you a function which is only be non-zero at x equal to 0. Okay, at x equal to 0, the size of this function is actually going to infinity. And on the other hand, all the other points at x not equal to 0, the delta function is equal to 0. Okay? So that's actually the kind of function I was talking about. And the area of this function, if you do an integration over minus infinity to infinity over x, okay, the integration of this delta function, the area is actually 1. Okay, so that is actually the kind of function. So it's actually a really, really narrow function. Okay, very narrow, very narrow, very narrow. But the area is finite, which is 1. Okay, so you can have a square. You can actually start with a square pulse, for example, or square function, and you can actually make the width of the square narrower, smaller, and smaller, smaller, go to 0. Then what you are going to get is actually the delta function. Okay, so that's actually how we understand this delta function. Okay. All right, really quickly, and also we would like to use a few formulas which are documented here. So if I do an integration from minus infinity to infinity, exponential I omega minus omega prime t over dt, which is integrating over time t here, and divide the whole formula by 1 over 2 pi. Okay, what I'm going to get is a delta function, which is a delta function of omega minus omega prime. Okay, so that means when this delta function functional form tells us that when omega is equal to omega prime, then this function is actually like going to infinity, and only when omega equal to omega prime, this function is non-zero. In the other place, this function is always 0. Okay. And this strange integration actually give you this delta function. Okay, so that's the first thing which we will use was one useful formula. The second thing, which is actually just what just I talked about, if I do an integration over minus infinity to infinity delta x dx, then basically you get 1. Okay. The third one is actually kind of interesting. Okay, let's take a look. So if I do an integration over from minus infinity to infinity, delta function x minus alpha. Okay, let's look at this delta function first. This function is only non-zero when x is equal to what? Yeah, when x is equal to alpha. Only when that happens, this is actually non-zero. Okay, if you multiply this delta function to some function which is f of alpha and integrate over alpha from minus infinity to infinity. Okay, and that means that when alpha is equal to x or x is equal to alpha, this integration gives you non-zero result. All the other place, you will get 0, right? The interesting thing is that if you do this integration, what you are going to get is that, okay, when I integrate over alpha only when alpha is equal to x, this thing is non-zero. Therefore, what you are going to get is you get only one point out of it, which is actually f of x. Okay, so that's the intuition about this formula, etc. Any questions related to those formulas? Sorry. Yeah, can you repeat? The first integral. Yeah, this is actually pretty complicated, so it will take a few, like 10, 20 minutes to explain that. Yeah, but let's just take the words from the math department. We trust it. Okay. All right. So once I have those formula, I can now demonstrate you how I can actually extract a C as a function of omega. Okay. So this is actually the goal, right? So don't forget what we are doing. What we are doing is try to extract what is actually C of omega, so that actually we can actually finish this formula, right? So how do we do that? So suppose if I evaluate this function, 1 over 2 pi minus infinity to infinity dt ft exponential I omega t. Okay, if I evaluate this function, okay, this is coming out of nowhere, right? So coming out of Yen-Jie's hand, maybe, I don't know, okay? Suppose if I evaluate this function, okay, and now I have ft here, right? I can replace ft by this interesting formula, right? If I do that, then basically I get 1 over 2 pi minus infinity to the infinity dt minus infinity infinity c omega prime exponential minus I omega prime t. And that is actually integrating over d omega prime. Then I have, so this is actually the f of t, right? This is actually f of t. I'm just replacing that formula into this integral. And then I have the rest, which is exponential I omega t. Okay? And of course, I can continue and collect all the relevant terms together. This is actually equal to 1 over 2 pi minus infinity to infinity. I collect all the terms related to omega prime to the left-hand side. Okay? Basically, what I get is C omega prime d omega prime. Right? This is actually coming from here, except, okay, this is actually coming from here, okay? And I have another integral which is from minus infinity to infinity, this time integrating over delta t, dt, right? And I have dt here, exponential I omega minus omega prime t. So basically, I'm collecting these two terms together, then that become exponential I omega minus omega prime t. Okay? So basically, no magic happened, but I'm just rewriting things and rearranging things from this formula to that formula. Okay? Then, if we look at this formula here, and the formula sheet we have. 1 over 2 pi minus infinity to this integration over t exponential I omega minus omega prime t. That will give you delta function, which is delta omega minus omega prime, right? Therefore, I can continue this calculation here. That is going to give you minus infinity to infinity. I identify this part, and this part to be the delta function. Therefore, what I get is minus infinity to infinity, C omega prime, delta omega minus omega prime, d omega prime. Right? Am I going too fast? Everybody is following? Okay. So you can see that what we have been doing, I use this formula coming out of nowhere. I replace f by the formula I was writing there, right? And then I collect the terms I like together. That's all I did. And then I found that, one part of the formula is actually the delta function. Okay, then I put the delta function here. And then finally, I use the third formula here, which I have related to delta function. And I found that, if I do this integration, I know how to do this integration even without knowing the structure of C, right? This is actually just changing the omega prime to omega, right? That's actually what this integration actually does, right? Therefore, I get C omega. Look at what we have done. What we have done is that we have proved that this formula coming out of nowhere to be a continuous version of mode picker. You remember the Fourier decomposition before? We were using the orthogonality of the sine function, and I can do some kind of fancy integration to actually extract Am from one of the, which is associated with one of the normal mode, right? What we are doing here is actually a continuous version. Now omega is actually continuous. And I now using the orthogonality of the exponential function. If I do this integration, that will only give you non-zero value when omega is equal to omega prime. It's exactly the same thing, right? Then I can construct an integration like this, and that will give you the resulting C as a function of omega, which is like the amplitude of one of the associated harmonics exponential I omega t. Okay, so in short, from this exercise, we have shown you that C of omega can be extracted using this formula 1 over 2 pi minus infinity to infinity dt f of t exponential I omega t. That's actually how we actually can determine all the amplitude associated to a specific exponential function. Any questions so far? Okay. So if no question, then we can actually continue. So let's actually go back to the original question which we were posting. Okay. So we have a problem related to the transmission of information. So this is actually where we got started. Okay. If I send the square pulse on a dispersive median, okay, then I have some trouble, which is that this pulse is going to disperse and become wider and wider. It's changing as a function of time, as a function of distance it travels. That's not cool, right? All right? So therefore, what are we going to do with this? There was a very smart idea which was discovered a long time ago during maybe World War I and widely used in World War II, which is the AM radio. What is AM? It's actually amplitude modulation radio. Okay? This smart idea is the following. Okay? I will describe it before we take a break. So this smart idea, AM radio, is the following. Okay? If I have some kind of information, which is Fs, T. S here means signal, okay? If I have some kind of information I would like to send, I can send it by oscillating one end of the the string, and this is what I want to send, okay? And there are two ways you can send this ff's function. The first one is actually what we did before. I send it directly. I just said, okay, if I want to send this function, then I just isolate the string according to the functional form, okay? Yen-Jie just have to be really careful, right? So that you can send this function. And that fails miserably, right? Why? Because all the components which actually produce the fs function, okay, in this case, it's a square pulse. All those components are traveling at different speed. Therefore, the information will never get there because of the dispersion, okay? So now, what should we do instead? Instead of sending fs as a function of t directly, what you could do is that I can now send f of t, which is equal to f of s t cosine omega 0 t, where omega 0 is a very, very large number, okay? And basically, look at what we have been doing. So that means instead of sending fs directly, I send fs, but modulated by a really high frequency function, cosine omega 0 t. And this will work. And you will only know that after we come back from the break, okay, which is 21st. Okay, let's take a 5-minute break. And if you have any questions, you can actually ask me here. Okay, so we will continue the discussion about and radio. Okay, so before the break, actually we introduced this one possible solution to solve this dispersive median problem is that I can now actually send, instead of fs as a function of t, which is actually the signal I want to send, I could send fs, but multiplied by cosine omega 0 t, okay? If I assume that fs is some really slow function, okay, slowly varying as a function of time, compared to cosine omega 0 t. Cosine omega 0 t is like a really fast function, okay? Oscillating up and down like crazy, really fast, okay? If I multiply fs by this function, what is going to happen? Okay, we are going to show you that actually that means I am going to only have non-zero C function, or say large contribution of C in the very limited range of omega. Okay, so we'll show that. So in a typical case, fs is really slow, which is like, for example, my sound, etc., is like at the level of 1 kilohertz. And you can actually design a system which actually multiply this fs by cosine omega 0 t. Omega 0 can be as fast as 1.1 to 30 megahertz. Okay? If you do this calculation, then you will find that, okay, the range of omega with sizable C omega is small. It's roughly equal to omega 0 minus omega s to omega 0 plus omega s, where omega s is the typical frequency in your signal, and the omega 0 is the typical frequency of the frequency of your cosine omega 0 t term, which is actually later you will recognize this as carrier. Okay? So what I want to say is that if I do this trick, what is going to happen is that the range of omega, which you have sizable contribution from C omega is the associated amplitude, right? Associated amplitude. It's going to be confined in a really small region from omega 0 minus omega s to omega 0 plus omega s. So that's the trick which actually make this problem solvable. How do we know this? Okay, that is because if I now, for example, I send fs equal to cosine omega st. Okay, if this is actually the signal which I would like to send, just a harmonic wave, okay, then what is going to happen is that I'm going to get ft is equal to cosine omega st cosine. So this is actually multiplied by cosine omega 0t, right? So I have cosine omega 0t here. Okay, I have cosine multiplied by cosine. Therefore, I have the equation which I prepared here, the formula of cosine alpha times cosine beta will be equal to that functional form, right? Just a reminder. Therefore, I can now write it as 1 over 2 cosine omega s minus omega 0 t plus cosine omega s plus omega 0 t. Okay, you can see that when I actually multiply two cosine functions together, then what I get is actually omega 0 minus omega s. Okay, you can actually put a minus sign there. It doesn't really matter. And the cosine omega 0 plus omega st times t, right? So therefore, you can see that the frequency, there are only two frequencies which contribute to the C of omega, which is actually these two frequencies. Okay, so that's actually why if you do this trick, you actually try to modulate your slow signal function by a fast carrier frequency. Then you are going to confine the effective range of omega into a very small range. Okay, why is that useful? That's actually what I want to answer to you, right? So suppose I have this crazy dispersion relation, which is omega as a function of k, right? You can graph it, and suppose it looks really crazy like this, okay? And if I set my carrier oscillation frequency to be omega 0, okay? And that will give you a corresponding wave number, which is K0. Okay, I hope you can see it. All right, that's the corresponding K0. Okay, before we actually multiply this function, okay, it is a slow function. It's not exactly one cosine function. So if you just have a cosine function harmonic wave, then you don't really need this trick, right? Because it's actually going to be traveling at the speed of some constant speed, right? It's a harmonic traveling wave. But if it's a slow, this is actually a slow function, but not really a single harmonic wave, then what is going to happen is that you are going to need a wide range of k value or omega value to describe fs. Okay? Then you are in trouble because now all the waves with different wavelengths are going to be traveling at different speed. Then you have this dispersion problem. Okay? On the other hand, if I multiply this function, this slow function, by a fast oscillating function, I am confining the effective range of omega into this small box. which is actually between omega 0 minus or plus omega s, right? This is actually omega 0 plus minus omega s. This is actually the range of the possible omega, which contribute to this resulting f of t. Therefore, the behavior of this function is actually much easier to understand. Okay? So if with that given there, suppose now I have a large difference between omega s and omega 0, then I can actually focus on a very small range in this dispersion relation diagram. Then I can write omega as a function of k, the dispersion relation, equal to omega 0 plus k minus k0, partial omega, partial k, evaluated at k equal to k0, plus higher order term, right? Basically, I can do this Taylor expansion, okay? And maybe it surprised you. You can immediately identify, this delta d omega dk is the group velocity. Okay, suddenly it shows up in the Taylor expansion of the dispersion relation. Okay, so if I focus on the region which is around omega 0, then I can actually rewrite omega in this functional form. Omega is actually equal to omega 0 plus k minus k0 times vg, which is the group velocity. Okay? So suppose this is happening, then now I can actually go ahead and really calculate the functional form for f of t. Okay? So suppose now I have this definition of t. The definition of t is equal to fs t times cosine omega t, omega 0 t. Okay? Or say I can actually write it in a complex form. Instead of writing it in a cosine omega 0 t functional form, I can write it in an exponential functional form, exponential minus I omega 0 t, okay, which is actually more convenient for the discussion. Okay? So what is going to happen if I actually do this calculation? Then basically, that's one example signal which I would like to send on the slides. So if I'm trying to send a progressing harmonic wave, then after multiplying by this exponential I omega 0 t function or cosine function, basically you get something which is actually oscillating really fast, which is actually the n signal we are trying to send through this medium. Okay, so we can actually identify this actually the structure. So this is actually the carrier, and this signal becomes the envelope in analogy to what we actually have discussed for the beat phenomena case. Okay? So now, if the omega range is really small, then I can actually write this down, write a functional form of omega in this functional form, or I can actually take out the k vg term, and the rest is actually going to be something like some constant a, where a is actually equal to omega 0 minus vg times k0. Okay, so basically I'm just taking out this k term here, and this becomes this term. Okay, with this formula, I can solve what would be the functional form for k, okay, as a preparation for what I'm going to do later. So k can be also expressed as omega over Vg, right? So basically, I just solve the k plus b. B is actually just some constant, right? Just for convenience, I can write b equal to k0 minus omega 0 minus divided by Vg. What we learn here is that if the range of effective omega is really small, around omega 0, then the relation between omega and the k become a linear function. Okay? Of course, it's not like still not like the case for the non-dispersive median, right, where omega over k is a constant. But at least it becomes a linear function, which is actually much nicer. Okay? So finally, with all those preparations we have done, we would like to show one important consequence. So what we are trying to do is to show that psi xt, okay, now I isolate the median, the string by this f of t, which I designed there. Ft is actually fs times exponential I omega 0 t. Okay, that's actually designed there. Okay, I would like to show that the resulting amplitude will be equal to fs t minus x divided by Vg exponential minus I omega 0 t minus k0 x. Of course, I need to take the real part of this, right, to go back to the real axis. Basically, I dropped the I sine omega t contribution. Okay? So this is actually what I want to show. Okay? Before I go through all those maths, let's look at the conclusion which we would like to draw before we actually really go through the maths. The conclusion which I would like to draw is that, okay, this is actually my envelope. Okay? My envelope is going to be traveling at the speed of Vg, which is the group velocity. That's the conclusion which I would like to draw from this exercise. And this thing is actually cosine omega 0 t minus k0x. Therefore, this is actually a harmonic wave. The carrier is a harmonic wave traveling at the Vp equal to omega 0 divided by k0. That's the kind of conclusion which I would like to draw from this exercise. Okay? Any questions about what we have discussed so far? Okay? Then, really, you have to hold tight and follow me really 100% focus, okay, because this is actually a complicated calculation. So now what I can do is now I need to express my fs in terms of c, right? So I do an integration from minus infinity to infinity, d omega, c omega, exponential minus I omega t. Okay, so basically I can write my fs in a functional form, which we introduced before. Okay, then my f function is actually equal to fs times exponential I omega minus I omega 0 t, right? So that's actually what we defined there, right? And this will be equal to minus infinity to infinity. I do this integration over omega c omega exponential minus I omega plus omega 0 times t. Okay, so there's nothing special. I just take my expression for fs, multiply that by exponential minus I omega 0 t, then that's actually what I get. Okay? Now, I can always, so since this is actually integration over omega from minus infinity to infinity, right? Therefore, I can always have the freedom to shift the origin, right? Okay, so that means f of t can be written as minus infinity to infinity d omega c omega minus omega 0 exponential minus I omega t. Okay, then we can see that there's a fixed relation between c of the f function and the c of the fs function. Okay, so far everything is exact. I haven't made any approximation so far, right? So now I can take this function and propagate that to all x, right? In the other word, I can now take this ft and write down the psi is a function of x and t. Okay, so that means all the different components are traveling at different speed. So basically, I can write it down like d omega c omega minus omega 0 exponential minus I omega t exponential I k x. Right? K is actually a function of omega. Okay, any questions? So that's actually just identical to what we actually have done before, right? So now I can go from f of t to psi. Okay, if you are following me. All right? So until here, everything is exact. You have all the problems you have, like this dispersion, etc. Because all the little components, as you can see here, can be traveling at different speed, right? Okay, so now what I could do is that if I assume that c omega is only sizable at the small range around, it's only sizable around omega 0. Okay, if now I take this assumption and propagate into this formula, okay, then I can write this psi function roughly like minus infinity to infinity d omega c omega minus omega 0 exponential minus I omega t exponential I. Now I can take the formula, which I actually did the approximation, right? Around omega 0, k can be written as omega over Vg plus b. Right? This is actually where I take the approximation. Only consider the first order in the Taylor expansion. Okay? So you can see now here it's not exact anymore, but now I write approximate functional form for k omega. Okay? So what I'm going to get is omega over Vg plus b. Okay? Multiplied by x. Okay? Any questions? Okay, now I have the approximation. And of course, now I can gather all the terms related to omega together. I'm getting minus infinity to infinity d omega c omega minus omega 0 exponential minus I omega t minus x over Vg exponential I bx. Right? So basically, I merge in this term and that term. This term and that term will give you this term. Okay? And what is actually the rest is the exponential I bx. Okay, we are almost there. So now I would like to use this board. So I need to erase that. Okay, so now I continue from here, and I can now again change the origin of this infinite integral, right? so that this can be rewritten as minus infinity to infinity d omega c a function of omega exponential minus I omega plus omega 0 t minus x divided by vg, okay? And the exponential I dx, okay? So what I count from this board to that formula, if you are following me, we are almost there, is that I'm changing the origin again so that omega minus omega 0 become omega, become the new omega. Okay, is everybody accepting this fact? Okay, and that means the original omega will become omega plus omega 0. Okay, I'm trying to go really fast, really slow. Okay, so that everybody can follow. Okay, I hope you are following. All right. Then now I can actually redistribute it, rearrange all those terms, and the magic will happen. Okay, so that means rearrange all those terms, minus infinity to infinity, the omega, c omega, exponential minus I omega, t minus x divided by vg, exponential minus I omega 0 t, exponential I omega 0 over Vg plus Bx. So basically, there's really no magic. What I'm going to do is really to rearrange all those terms. So this term is actually rearranged so that it's now omega times t minus x over Vg is an independent exponential term. Okay? And I actually extract this term times t to be written here. Okay, I'm just rearranging things, okay? I'm not changing anything. And finally, I can merge this term and that term and become this function field. Okay? I can immediately recognize that after this rearrangement, okay? It's just rewriting the formula, putting all those terms in different places, okay? Of course, you can actually review this part of the lecture in the lecture note later. But basically, why not doing anything fancy, but rearranging things over in different places? Then I can actually quickly identify what actually I'm trying to integrate, okay? So this integration is over omega, right? Therefore, all those terms are not related to omega. Therefore, they are just some terms which are sitting there, doesn't participate. And if you focus on this part, okay, what is this? If you compare that to the original equation, which I have here, if you compare that to the original Fs equation here, you can immediately identify that actually that's a function of Fs. Original, this function Fs is a function of t. And I'm going to that board. Now, this is actually Fs, but t minus x over Vg. Surprisingly simple. Okay? Now, let's look at the right-hand side, this mass here. Okay? This is actually K0, which actually you cannot see it anymore. It's in the back of this board. And if you combine these two terms, basically what you get is exponential minus I omega 0 t minus K0 x. So look at what we have done. I got started with this Fourier transform functional form of Fs. I multiply Fs by cosine omega 0 t and go to the complex notation. It becomes exponential minus I omega 0 t. If I multiply that, I get my f function which is like this. You get the additional term there. I rearrange things and change the origin, and I can rewrite the ft in this functional form. And I can have a relation between the c related to fs to the c related to f of t. I propagate ft over the full space and obtain my psi, which is the amplitude as a function of place and the time. Until here, everything is exact. Then I have introduced an assumption, which is c of omega is only sizable, only contributing around omega 0. Therefore, I can do an approximation form for the k function, which is actually this functional form. Okay? Then I just do the integration. Then I found out, interesting, this psi, okay? This psi is actually, oh, okay, it should be taking the real part of this thing. This psi have two components. The first component is fs, which is the original signal you put in, the signal you want to send. It's actually progressing at the speed of group velocity. Okay, so now you understand what does group velocity mean, right? That's the speed of the signal you want to send in the n radio, okay? And this thing is actually modulated by exponential function, which is actually propagating at the speed of Vp equal to omega 0 over k0. So the carrier still, after you actually include many terms constructing the f function, the psi, which is the amplitude, okay? The trick is that only the omega value around omega 0 contribute. If that happens, then you can see that there are two structures actually propagating at different speed, and you can actually understand this structure independently, okay? That means your signal will not be distorted if you send it in this way. But the difference is that the speed of the signal you are sending is actually at the speed of group velocity. Okay, that is actually an amazing fact, which actually enables us to send signal over thousands of miles away from the source. So what is actually done is actually that suppose you have some kind of radio station, you can send the radio, and the radio will go over the place and got refracted by, I don't know, sphere, the atmosphere on Earth, got refracted, and the receiver from some place which is really distant from the source can still see it without any dispersion, as we show here. And it's actually going to be propagating at the speed of group velocity. So you may not actually believe that, right? How about we do a simulation like what we did before with NIT wave? So this is actually the example which we did last time. We have an NIT wave. We decompose that into many pieces, and then see how it evolved as a function of time. This is actually without dispersion. Therefore, everything is perfect, right? All right. So now I would like to introduce some excitement there. Okay. If I have dispersion, like 0.1, alpha is equal to 0.1, and see what will happen. Then just a reminder that things will not go super well. Wait a second, what I'm doing? This is actually still without dispersion. Sorry for that. This should be, oh wait. Okay, so let's take a look at the triangular case. This is now with dispersion. And you can see that as a reminder, as a function of time, the shape of the signal which we would like to send is actually changing as a function of time. And after a few thousands of miles, you will not even recognize the original structure we put in. Okay, so that's the trouble we are actually facing. Okay, you can see that it's getting wider and wider, etc. So now, what will happen if I send this kind of signal? This is a signal which will have some kind of shape. You can imagine that there's some kind of envelope, and I am now doing the calculation to actually map all the individual components, and now I'm going to propagate through the median. And the blue is the original non-dispersive median situation, and the red is actually the propagation in a dispersive median. You can see the propagation in a dispersive median is faster because alpha is actually larger than 0. So it's actually, in this case, it's 0.1. And you can see that the red cosine omega 0 t modulated signal is progressing, okay? And the shape of the envelope is not changing. You can see that, right? So it's very different from what we actually see before with a single triangular pulse, right? Now you can see that, only when n gets very large, I start to be able to fit all those little structures, right? That means the n value, or say the omega value, which I need, is really narrow, a very narrow range, which actually match with what we have been doing. And now I start to propagate all those things, and you can see that the red is actually traveling faster than the blue, which is what we expect. And you can see now at the instance they actually overlap each other, you can see that the envelope, the shape of the envelope is still the same. It's exactly what we actually predicted. And that actually brings me to the end of my lecture. We have understood how the AM radio actually works. And next time, we are going to talk about uncertainty principles. What the hell? What happened? And believe me, they are actually connected to each other with uncertainty principle is actually highly related to wave and the vibrations. Thank you very much, and let me know if you have any questions.